Okay, so we're going to be working through this review. With some of them, we're going to focus more on the actual question, and for others of them, did I just mess that up? Dang it. Okay. And for other ones, we'll kind of focus more on just the work that's involved. So, let's start with number 1. This one's very visual, because this one's asking about limits. So here we have a function, piecewise function, and what do we notice is going on at, let's see, where's my limit? Where am I looking at for my limit? I'm looking as x approaches 3. What's happening at 3? What do I have going on there? A jump. I have a jump discontinuity. So, go ahead and tell me about this limit, part C. There is no limit. It doesn't exist, right? That limit won't exist because it's a jump discontinuity. Because it's a jump discontinuity, your function is approaching 2 different values from the different directions. So I already know that part C, that's not going to exist. But if I look at each of these, if I look at these directional limits, right? So as part A is as x approaches 3 from the negative direction, that's coming from the left side. Negative direction is the left side. So what is my function is approaching as I approach from the left side? I'm approaching 5. Very nice. From the right side? 2. Usually if it specifies a direction, I'm trying to think of a situation where the limit wouldn't exist. If it specifies a direction, the limit's going to exist because you can look at your graph and see where it's actually going. And sometimes that answer might be infinity if you're working with an asymptote, but if it specifies a direction, the limit's going to exist. But because we're approaching 2 different things from the different directions, if I don't specify a direction, right, because this is a jump, if I don't specify a direction, the limit does not exist. Okay. Any questions about that one? Kind of the graph side of limits. Okay. Well, perfect. Let's move on. Next question. This one's evaluating the limit without a graph. So using algebra, so we'll just kind of do this one over on our little whiteboard over here. So, and you're going to see I've already done all the work, but every time I open it up again, it regenerates the questions. So sometimes my numbers will be different from what it actually shows on this little test thing. Okay, limit. As x approaches, so this was my problem, as x approaches 12, of x squared plus 3x minus 180 over x squared minus 144. Remember, when we are algebraically evaluating limits, what's a great first thing I can do? Go ahead and plug in, right? Plug in the value I'm evaluating the limit at, right? Plug in the x value and see what happens. Turns out, though, if I plug in 12, I get, I don't want the highlighter anymore. I get 0 over 0. What do we call that again? Indeterminate. So this is my indeterminate result, indeterminate value, which means I've got to go mess with this some more. I've got to algebraically manipulate it to see if I can break it down and come up with an actual answer from it. So what do you think? What's my strategy for this one? Factoring. This one's all about factoring. If I can factor this one, then I should be able to evaluate my limit. So, by the way, I should keep track of what number we're on. This is number 2. Okay. What is the denominator factor to?
X minus 12, x plus 12.
Right, that's a difference of squares. Everybody okay with that? X minus 12, x plus 12. Difference of squares. Numerator. Well, which of these, so we've got my denominator all set up. Looking at that denominator, which of those terms do I want to cancel out in the denominator? What am I hoping is going to cancel out here?
X
Well, which one? The x plus 12 or the x minus 12?
Minus.
The x minus 12. The x minus 12 is the one causing my discontinuity. Remember, x is approaching positive 12. If I plug in positive 12 to x minus 12, I get 0, and that's what's causing the discontinuity. The x plus 12 isn't the problem. 12 plus 12 is 24. We're good to go. X minus 12 is my problem. So what can I kind of assume is going to be one of my factors up here?
Negative.
X minus 12. I can already assume that x minus 12 is going to be one of my factors. In fact, why did I put that on the left side or right side? I ought to just put it on the left side over here. So that's good. Half of my factoring is already done. All I need to figure out is what would I multiply x minus 12 by in order to get this whole x squared plus 3x minus 180? I already know, I know it's going to be just an x, right? My x squared term doesn't have a coefficient, so I know that's just going to be an x.
15.
Yeah, does 12 go into 180 evenly? Yeah. 15. Positive or negative? Positive. And let's just make sure that works. What is 15 minus 12?
3.
Positive 3. Yep. Oops. I wanted to highlight that. Ugh. Positive 3. Okay. Minus 12 plus 15. That gives you that positive 3x. So sure enough, that works. And you can always check your answer by actually multiplying that through, see what you get. But you should, I believe that's correctly factored. So now that we've factored it, right, the x minus 12s cancel out, which is exactly what we wanted to happen. We wanted the discontinuity to cancel out. And so now what are we left with? We're left with the limit as x approaches 12 of x plus 15 over x plus 12. Do I have a discontinuity at 12 now? No, I've eliminated it. So now what can I do?
Plug in.
Just plug in 12 for x. And I get 27 over 24, which is what? 9/8? Very nice. Questions about this one? Okay. Okay, let's move on. Okay. Question 3. So suppose a fashion company determines that the cost in dollars of producing X cell phone sunglasses is given by this cost function, negative 0.05x squared plus 60x. And then it asked me to find this C of 301 minus C of 300 over 301 minus 300. Well, what does that look like? What does that C of 301 minus C of 300 over 301 minus 300? What does that look like? Yeah, Braden.
Substituting x for 301 and 300.
So absolutely, right? That's what this function notation is actually telling me to do, right? C of 301 means I'm going to substitute 301 in for my cost function. So that's how I'm actually going to calculate it, right? C of 301, plug in 301 into your function. C of 300, plug 300 in your function, and then subtract those two values. And then what's 301 minus 300? What am I going to get in the denominator? Just 1, right? But what does this look like? Change in y over change in x. Right. This is a rate of change. That's exactly what this is. It's a rate of change that I'm going to use to actually answer part B. Oh, great. I don't actually want to put in the time to answering this one, so I'm just going to purposely get it wrong. Yes. Check answer. I know it's wrong. I know. Because I now want to look at this one, interpret the result. So in that case, which one of these is correct?
it tells us how much it costs to make one more item after making 300.
Okay, so why one more item? Because there's a few of these that, like, look at A. A sounds pretty similar. It represents the average cost per item to produce 300 items. Why are we looking at B and not A?
Because it's the change between the 300th item and the 301st item.
Right. This change in X is only one. It's 301 to 300. If we were looking at the average cost per item to produce 300 items, your change in X would be from 300 to 0. Right? But the fact that we're just going from 300 to 301 tells me this is the average cost to produce one more item. The average cost to produce one more item after I've already made 300 items, right? We're starting at 300 and we're going to 301, so I've already made 300 more, 300 items. Very nice, very nice. Okay, moving on. Number 4, also very graphical here. List the points in the graph at which the function is not differentiable. Thoughts? Pace?
All but x0 and x5.
Why? What's special about x0 and x5 that tell me, yeah, it's differentiable there?
The best way I think about it is that there's just nothing weird going on with
There's
it.
nothing weird going on. Another way you could say it is, my function is continuous there, right? My function is continuous as x0 and continuous at x5. Now, to be clear, right, my function is still continuous at x3, but what's going on at x3?
Same function thing.
I have this weird angle going on at x3. If I have an angle, I can't take the derivative at an angle. Okay. So sure enough, it's not differentiable in x3, and every other point besides x0 and x5, right? x1, it's not continuous at x1. x2, not continuous at x2. x4, not continuous at x4. So anywhere that it's not continuous, and x1, anywhere that it's not continuous, it's not going to be differentiable. And if I have an angle at like x3, also not differentiable. Okay. Awesome. Okay, now we get into just some basic derivatives, making sure we know our derivative rules. Okay, so here we have 5x to the negative 3. What's my derivative? Even I have a negative exponent, can I still use power rule? Absolutely, I can still use power rule. So I'm going to bring down the negative 3, then subtract 1 from the exponent. And I get 5 times negative 3, x to the negative 4, which of course simplifies to negative 15, x to the negative 4. Okay. So that one's just a really quick example of power rule, using power rule. Okay, question 6. Ooh, question 6 is a good polynomial. Nice long polynomial. Okay, we've got y equals 3x cubed minus 11x squared plus 24x plus 1. Well, a polynomial just gives me more opportunities to use the power rule, because I can use the power rule with each of my terms. And then just remember that each of these, what do I do with each of these coefficients?
Can it just get set outside?
Yeah, just leave them, right? We're gonna keep those coefficients and multiply whatever I get from power rule to those coefficients. So I get 3 times the derivative of x cubed, which is 3x squared, so 3 times 3x squared gives me 9x squared. Minus 11 times the derivative of x squared, which is just 2x. So 11 times 2x gives me 22x. Derivative of 24x?
24.
Right. Since now I've reached a linear function here, the derivative of a linear function is just its slope. Derivative of plus 1?
0.
Derivative of any constant is 0. Very nice. Okay. Nice and easy. Question 7. The 5th root of 9x. How do I take derivatives of roots?
Make it a fraction.
You make it a fraction exponent, right? I can just rewrite this one as 9x to the 1/5. Sorry, that's not very pretty. Okay, so I can write this as 9x to the 1/5. Awesome. And then I can just take my derivative like normal. Although, because I have 9x in my parentheses, what does this derivative now require? Chain rule. Right. So if I use chain rule here, I do the derivative of the outside function, keep the inside function the same. 1/5 minus 1 gives me negative 4/5. But then I have to multiply by the derivative of the inside function, which is just 9. Right, derivative of the inside function is just 9. Very nice. Okay. But speaking of the fact that, anytime you see a root, remember you can rewrite that root as a fraction exponent. That also applies if you see something like this. It doesn't have to be 1 on top. It could be any constant on top. But how do I rewrite something like this?
X negative 1.
Right. If you ever have a power function in the denominator, you can rewrite that using a negative exponent. And we already saw how if you have a negative exponent, you still just use power rule. Okay. So just a little reminder there. Okay. Number 8. What does this derivative require? Quotient rule. Yep. This requires quotient rule. Once again, you will have the quotient rule on your formula sheet, so you don't have to memorize quotient rule. It's there. And just to help you make sense of how the notation they use on it, they use n of x for the numerator. So in my case, the numerator function is just x. And they use d of x for the denominator function. That's x to the negative 1 plus 3. In order to use quotient rule, I needed the derivative of both of those. Derivative of the numerator is just 1. Derivative of the denominator. I have to use power rule for the first piece, but the derivative of 3 is just 0. So I get negative 1 x to the negative 2. Now I can put this all together using quotient rule. So the quotient rule is the bottom function times the derivative of the top, which is just 1, minus the top function times the derivative of the bottom, which is just negative x to the negative 2, over the bottom function squared, so x to the negative 1 plus 3 squared. Now remember, you'll notice there's no blue text next to this little submission box. There's no blue text next to it, meaning you don't have to simplify with your answer. You can just type this in the way it is, and it'll give you credit. And the reason I say that is because I don't want you guys to miss points on the exam because you tried to simplify and you messed up your simplification. Okay. Remember, like these homework and reviews are nice because you can redo the problem as much as you need to. That's not going to be an option on the exam, right? As soon as you submit that answer, it's final. I guess you can go You can go back and look at answers again before you actually submit your exam. But once you submit that exam, your answer's final, right? You don't get to check your answer first and then redo it. Okay. So number 8's a good practice for quotient rule. Question 9. What does question 9 use? Chain rule again. You got a function inside of this other function, right? Where you've got y is equal to 12 minus x raised to the 67th power. What's my outside function? Yeah, something to the 67th power. Remember, we often use u as my dummy variable. So I can say y is equal to u to the 67th. And what is that inside function? 12 minus x. So when I use the chain rule, I take the derivative of my outside function, which is 67u to the 66th. But what is u? U is your inside function. So I'm just going to keep that inside function the same, 12 minus x. So I have 67 times 12 minus x raised to the 66th power times the derivative of your inside function. Well, what's the derivative of this inside function right here? Just negative 1. Right? And that's because u prime is equal to negative 1. Very nice. Questions about chain rule? Cool. Okay. Moving on. Question number 10. This one. What does this function require in order to take the derivative? What does this derivative require? Product rule. This requires product rule. And when you're working through product rule, it's also going to require chain rule. Right. So when I'm using product rule here, my first function is x. My second function is this x cubed plus 2 to the 4th. Derivative of your first function is just 1. Derivative of your second function. This is where it requires chain rule, right? To go from here to here, you need chain rule. And you get 4, keep the inside function the same, to the power of 3 times 3x squared. Okay. Why am I doing all this? Once again, because I need to use product rule here. Because you have x, you have a function x times this other function, x cubed plus 2, all raised to the 4th. You've got two different functions that are being multiplied together. That's why I'm using product rule. So when you put it all together, you get, g times f prime, which is just x cubed plus 2 to the 4th times 1, plus f times g prime. So you get 4 times x cubed plus 2 raised to the 3rd power times 3x squared times x. Cool. Questions about product rule? Questions about this one? Okay. Moving on then. We are going a little fast, but that's because I want to try and cover as many of these as possible before the end of class. Okay. Aha! This is a good position function, right? This is a good position, velocity, acceleration type problem. So, an object is dropped on a certain Earth-like planet. It's good to know. The distance it falls in t seconds, assuming that air resistance is negligible, is given by the following position function. So, we have s of t equals 17t squared. Suppose that a medic's reflex hammer is dropped from a hovering helicopter. Find how far the hammer falls in 4 seconds. So let's just focus on part A. How far does the hammer fall in 4 seconds? Well, what is that question asking for? Position, velocity, or acceleration?
Distance.
It's just talking distance. It's just talking position. So I don't need to take any derivatives yet. All I'm doing is plugging 4 into my position function. So part A is just S of 4. Okay. Part B. How fast is the hammer traveling 4 seconds after being dropped? Well, what is that asking you about? Velocity. Not acceleration, velocity. How fast is it traveling? That's velocity. How fast is it traveling after 4 seconds? So that's just asking me, what's the velocity after 4 seconds? Remember, velocity is just the derivative of the position function. What's the derivative of the position function? 34t. All right, here, actually, you know what I should do? I should write that up here. Right. Derivative of the position is 34t. And so, okay. Last, the hammer's acceleration after it's been falling 4 seconds. Well, that's obviously asking about acceleration. And if you remember, acceleration is just the double derivative, the second derivative. If I take the derivative of 34t, I'm just left with 34. Notice, interesting, there's no place to plug in a value. So what do? It's just 34, right? It's your acceleration is constant. It's always 34 no matter how much time has passed. Very nice. The big idea with this problem is just remembering that velocity is the derivative of position. Acceleration is your derivative of velocity, or the second derivative of your position. That's really the big idea with this problem. Okay, moving on. Number 12. Now we get into chapter 2. Extreme values. Relative maximums, relative minimums. So find the relative extreme points of this function. What's the big idea here? What's the process?
You have to find the derivative.
Take the derivative, set it equal to 0. Remember, you're trying to find those critical points because your relative minimums and maximums occur at those critical points. So I'm going to take the derivative and set it equal to 0. What's my derivative of? Well, here, let me just write the function out first. So x cubed plus 2x to the 4th. What's my derivative? 3x squared plus 8x cubed. And then like we said, I'm going to take the derivative and set it equal to 0. I want to know where the function flattens out. And then I'll solve for it. How do I solve for something like that? Factor. Can I factor it all? Can I factor this function at all? I have 2 different terms. Do any of those terms share certain things? Yeah, both of them have 2 x's in it. So I can factor out an x squared. And I'm left with 3 plus 8x. So what are my critical points?
0 and
My critical points are x equals 0 and, I got to solve for that, right? 3 plus, here, I'll do that over here in blue. 3 plus 8x equals 0. Subtract 3 from both sides, you get 8x equals negative 3, x equals negative 3/8. Very nice. Okay, so I have my possible relative minimums and maximums. How do I determine if they're minimums or maximums?
the original function.
Plug them into the original function. That'll tell me what the y values are. But remember, that's really only helpful if I'm talking absolute max and absolute min. It's not that helpful if I'm only talking about relative minimums, relative maximums. So how do we do it with relatives? Yeah.
You plug the numbers around them into the derivative.
Right. This is where I make that whole number line thing. I make my number line. This is the first derivative test, right? I make my number line, put my critical points on the number line, and then test points inside of those intervals. Where do I test them? I test them with the first derivative just because I'm looking at whether the function is increasing or decreasing within those intervals. Okay? So let's test positive 1. What do I plug that into?
3x squared plus 8x cubed.
Yes, the derivative. I'm going to plug that into the derivative. What is g prime of 1? Well, 1 squared is 1. 1 cubed is 1, so I'm just left with 3 plus 8, which is 11. The important part about this is that it's positive. So I'm left with a positive value, which means my function is increasing. If your derivative is positive, your function's increasing. Okay, well, let's try negative 1. What is g prime of negative 1?
Wouldn't that go on the other side of negative?
Oh, you're right. Whoa. I forgot. I forgot how small our other critical point was. Oh, darn it, man. Negative 1 was going to be so easy. Okay, negative 1/8. Negative 1. Still not super fun. For this one, the calculation's not going to be really that fun, so instead I'm going to come look at this form of the derivative. That's still the derivative, right? If I plug in negative 1/8, what happens to this term? Positive or negative?
Positive.
I'm left with a positive times, what about this term? If I plug in a negative 1/8, what happens to that term?
Positive.
Positive. Because what's 8 times negative 1/8? Negative 1. What's 3 plus negative 1? A positive 2. Right here. In fact, I should actually write. I get negative 1/8 squared, which I know is going to be positive, times 3 plus 8 times negative 1/8. And like we just saw, that ends up being a positive because that's a positive 2. So this interval is also positive, which means I'm also increasing for this interval. What does that tell me about 0? Is it a relative min? No. Is it a relative max? No, it's neither. 0 actually ends up not being either a relative min or a relative max. So now it's down to negative 3/8. What is negative 3/8? Well, now I can use negative 1, right? Oh, and this was negative 1/8. So what is g prime of negative 1? I get positive 1. I'm using this one again. So I get positive 1 because negative 1 squared is positive 1. And then when I plug in negative 1 over here, I get 3 plus 8 times negative 1, which of course is going to be negative, right? You've got 3 minus 8. It's negative 5. So this one's positive. This one's negative. So overall, you end up with a negative value, and your function is decreasing over that interval. Okay. What does that mean about negative 3/8? It's a relative minimum. So for this first one, I already know that there is a relative minimum. So the tough part about that is this one has a lot of blue text. Let's read that blue text. Simplify your answer. Use integers or fractions for any numbers in the expression. Type an ordered pair. So this does want both the x and the y value. Where do I get that y value? Plug in negative 3/8 into my original function. Ugh, man. Negative 3/8 equals negative 3/8 cubed plus 2 times negative 3/8 to the 4th power. Okay. And I'm left with negative, let's see, negative 27 over, what is 8 to the third power? 512, negative 27 over 512 plus 2 times, now I have to raise all negative 3/8 to the fourth power. Well, when you raise it to an even power, that negative cancels out. And so I'm left with 27 times 3 is 81 over 4,096. I can't, the fun part about this problem is you can't just put that in as your y value. You have to simplify it. You have to simplify this y value into just one single fraction. So I'll go ahead and distribute the 2 over to this 81. What's my common denominator if I have 512 and 4096? This is the hardest part about this simplifying, is finding this common denominator. It ends up being 4096. Please don't just multiply 512 and 4096. Your answer is going to be massive. So the reason why your common denominator ends up being 4096 is because this is just 8 to the fourth. This is 8 to the third. So the only thing I'm missing is one more 8. So to get my common denominator, I can just multiply this by 8 over 8. And I'm left with negative 27 times 8, negative 216 over 4096, plus 2 times 81 is 162 over 4096. And once you have the common denominator, that's really not too bad, because that's just negative 216 plus 162, and you end up with negative 54 over 4096. I can simplify that, of course. Both of those are divisible by 2. So I get negative 27 over, what is 4096 divided by 2? 2048. I can't go any farther than that, though, because this is just 3 cubed, and this is 2 to a bunch of powers, so no common factors here. Of course, your numbers are going to be different, but the pattern of how you're going to simplify this is going to look very, very similar. Okay? So even though your numbers are going to be different, you can kind of still follow this same pattern. Okay, so let's go ahead and put that answer in. Make sure we got the right thing. So my y value is negative. Backspace. Fraction negative 3 over 8. And my y value is negative fraction 27 over 2048. Very nice. The reason why I wanted to make sure and do that is because what's my relative maximum? There is none, right? We only had the 2 critical points. One of them was a minimum, but 0 was neither. It wasn't a minimum or a maximum, which means I'm left with no other possibilities for a relative max. There is no relative maximum. So now let's see if we can graph the function. The zoom is a little messed up here. But the big idea here, what am I looking for? I'm looking for a graph that flattens out at 0 and flattens out at negative 3/8. But what should be true at negative 3/8? Do I have a max or a min at negative 3/8? I have a minimum at negative 3/8. And what's happening at 0? 0, you can kind of see it in a few of the examples. Something like that is happening at 0, where it's not a minimum or a maximum, but it's still flattening out. So which of these match that? A. Right. B and C don't work because they're putting the minimum and maximum at positive 3/8 instead of negative 3/8. And then D doesn't work because it's a maximum at negative 3/8, not a minimum. Very nice. Okay. Whew, we made it through that one. Okay. This one's also nice because it gives you multiple choice, so it gives you lots of different options to look at. For this one, you don't actually need all of this information. Let's just look at this first group of information that all deals with my x value of 3. F prime of 3 is equal to 0. What does that tell me? Critical point. I have a critical point at 3. Okay? Means I could possibly have a minimum or a maximum. The second derivative at 3 is negative, is less than 0. What does that tell me? The second derivative is negative.
It's concave up.
Concave down. If second derivative is negative, concave down. So if I have a critical point and I'm concave down, what does that mean? Maximum, right? And here I'll draw a picture down here to kind of help us visualize it. If I have a critical point, right, it's flattening out, and I'm concave down, I'm working with a local maximum. Local maximum. So that means I have a local max at 3. Well, let's keep looking. What about the next one? Sorry. What about a negative 1? F prime of negative 1 is equal to 0. Also a critical point. Negative 1 is also a critical point. The second derivative of negative 1 is positive, which means I'm concave up at negative 1. If I'm concave up at a critical point, it's a local minimum. Right. If you're concave up at a critical point, you're at a local minimum. Right? If I'm concave up and I've got a local minimum, and I've got a critical point, we're working with a local minimum. So I have a local max at 3 and I have a local min at negative 1. And I can actually stop there because there's only one graph that matches that. Local max at 3, local min at negative 1. That is graph A. Yep. You guys see that? Notice C and D are parabolas, which means they only have one critical point. But I know there should be 2 critical points. Awesome. How are we doing on time? 2:15, 30 minutes. Oh boy. I think we start. Okay. Question 14. Absolute extrema. Okay. Absolute extrema. And this one's interesting because look at that interval it gives you. It doesn't give me a closed interval. With this example, it gives me an open interval, which means I can't really test my endpoints, right? I can't test my endpoints here. If I do have a closed interval, remember you have to test your endpoints because your endpoints could possibly be your absolute max or your absolute min. Okay. But let's try this one out. If I'm looking for the absolute min or the absolute max, where am I looking? Where do I look for my absolute min or my absolute max? We already said I'm going to look at my endpoints, but where else? Critical points, right? I'm also going to look at my critical points. So I'm going to set this equal. I'm going to take the derivative and set it equal to 0. F of x is equal to negative 2x cubed plus x squared plus 8x minus 6. My derivative is negative 6x squared plus 2x plus 8. So I've taken the derivative. I'm going to set that equal to 0. Okay. How do I solve that? factoring, right? So here I need to factor again. All of my terms are divisible by 2, so I can just divide everything by 2 if I'd want. I get negative 3x squared plus x plus 4. That might help make my factoring a little bit simpler.
Do I have to put a 2 out in front?
Oh, well, yeah, you can, but if I have this set equal to 0, I could then divide both sides by 2. And what's 0 divided by 2? 0. So that 2 out in front doesn't actually affect your root, and you can ignore it. Oh, so factoring this. If you don't like factoring, what is always an option? Quadratic formula. So as long as you remember the quadratic formula, you're also welcome to use the quadratic formula here instead of factoring. But if we factor, one of these terms is going to have a 3, one of these terms is going to have a, and this one's going to be negative, and this is going to be a plus 1, and this is going to be a negative 1. Or negative 4. No, positive 4. There we go. Okay. Sorry, I skipped through that factoring, but hopefully you guys would be able to kind of do that on your own. This gives me 2 possible critical points, because now I can solve each of these, and I'm left with x equals negative 1 and x equals 4/3. Okay. Turns out, though, what can I do with negative 1?
It doesn't count. It's not within the interval.
It's not in my interval, so I can ignore negative 1. Negative 1 is not going to factor into this because my interval is 0 to infinity. And negative 1 is outside of my interval. So I don't have to worry about negative 1. I only have to worry about 4/3. Okay. So now we need to decide, is 4/3 an absolute max? Is it an absolute min? Or is it neither? Okay. Well, what happens if I'm going all the way to positive infinity? What's happening to my function as I let x get really, really big? What's happening to this function as x gets really large? What's my leading term?
Negative 2.
X cubed is my leading term because it's the highest power. What do you notice about the coefficient? It's negative. So if my highest power is negative, right? If the coefficient for my highest power is negative, then what's happening in my function as I let x get really big? It's going to negative infinity. It's decreasing. It's going to go all the way down to negative infinity. So, does this function have an absolute minimum? No, there is no absolute minimum because this function is going to go down to negative infinity. So my only option here is 4/3 the absolute maximum? Okay. And the only way you could maybe check that is just to make sure that if I plug in 0, what happens if you plug in 0? I know it's not technically an endpoint because it's parentheses, but if you plug in 0, what do you get? Negative 6. So this function on the other end is going down to negative 6. Well, is approaching negative 6. What happens when you plug in 4/3? This requires a little bit of math. But to save us some time, if you plug in 4/3, you'll get a positive value. You will get a positive value. And since that's bigger than what you're getting when you're plugging in 0, and we already know that this is going down to negative infinity, we do have a maximum at 4/3. Hello, come on. I have a maximum. Oh my goodness, come on. Whatever. We have a maximum of 4/3, but we do not have an absolute minimum. So I would select this option. Okay. Moving on. Okay. This is our optimization problem. Question 15 is our optimization problem. So we have a dumpster, a rectangular dumpster that will be twice as long as it is wide and must hold 26 yards cubed of debris. Okay. So let's just remember the process that we came up with for optimization. Find the dimensions of the dumpster that will minimize its surface area. So what are we trying to minimize? Surface area. That's the equation that I'm going to write. I'm going to write an equation for surface area. Okay. It's an open top, so I only have to worry about, so my surface area ends up being 2 times length times height plus 2 times width times height plus I only have to do length times width once because the top's going to be open. The top's going to be open. Well, what do we know about the length? What are my constraints?
Twice the width.
Twice the width. So my length is twice the width. So that's one of my constraints. Length is equal to 2 times W. What's my other constraint? If I use that, I get, and I think if I remember right, they want us to use X for the width. Okay. So what does that leave me with? That leaves me with 2 times 2x times h plus 2 times x times h plus 2x times x. I still have 2 different variables, and I don't want 2 different variables if I'm going to take the derivative. Just a reminder that x is your width. So what's my other constraint? It has to hold 26 cubic yards of debris. That is volume. So my other constraint is that the volume, which is length times width times height, right? 2x for the length, x for the width, and h for the height, has to equal 26. So now I can solve for h, and I get h is equal to 26 over 2x squared, which I, of course, can just simplify to 13 over x squared. And now that's what you can actually plug in for h. So that'll give you the surface area is equal to 4x times 13 over x squared plus 2x times 13 over x squared plus 2x times x, which is just 2x squared. Now you've got your surface area in terms of just one variable. There's a little bit of simplifying you can do to make your derivative a little bit easier, but your derivative is now in terms of one variable, and now you can go ahead and do what? What would I do next? Now that I've gotten my equation in one variable, take the derivative, set it equal to 0. Right? You're looking for critical points because you want to find a minimum or a maximum. So, right? So from here, you would just take the derivative, set it equal to 0. Very nice. Anytime you see that word optimization or minimum or maximums, that's your process. Take the derivative, set it equal to 0. Okay, moving on. Assume that revenue is in R of X is in dollars and X is the number of units produced and sold. For the total revenue function, R of X is equal to 12X. Find delta R, R prime of X, when X is equal to 90 and delta X is equal to 1. Remember, what is delta X?
changing.
Right, delta R. Delta R is just your exact change in your value. Okay? So for our problem, I'm going to calculate the revenue when? When X is equal to 90 and what else? And 91, right? Delta X tells me, well, how much am I going to change from my starting X value? So my starting X value is 90. Delta X tells me, and then I'm going to change it by just 1. That puts me at 91. And delta R is all about what's the difference between those two Y values. What's the difference between those two Y values? Everybody okay with that? So that's delta R. And then R prime of X is just taking the derivative. Okay. Number 17 is elasticity. So there's your demand function, is the square root of 300 minus x cubed. Find the elasticity. Okay. Elasticity just boils down to a formula, which is on your formula sheet, right? It's this negative x times your demand function. No, times the derivative of your demand function over your demand function. Okay. Hopefully you guys remember that from the chapter 2 project. Okay. So part A is just using that formula to come up with a function for the elasticity. Part B is just plugging 3 in. And then part C is interpreting that answer. Okay. So for example, for the problem that for the one that I did before, when I plugged in 3, I got 135 over 46. That's what I got. Based off of that answer, will a small increase in price cause the total revenue to increase or decrease? Well, tell me about this number. What am I paying attention to with this number down here? What am I paying attention to with this 135 over 46?
It's clear.
Yeah. How does it compare to the number 1? This is bigger than 1, which I can't remember. Is that elastic or is that inelastic? That's elastic, right? This is elastic. What does that mean? Raise the price or lower the price? Lower the price. You really should be lowering the price. So will a small increase in price cause the total revenue to increase or decrease? Decrease. You don't want to increase the price if you're elastic. Okay? If it were less than 1, then it's inelastic, and you do want to increase the price. But in our case, since that's greater than 1, don't raise the price. So that's a good little reminder about elasticity. Sorry, I'm going faster now because I took too long on the other ones. 18. Suppose that a price P in dollars and the number of sales of a certain item follow the equation that. But then both of them are functions of time. So what is this problem? We did a problem like this on your homework. This is implicit differentiation. Right? We have a function. That's in terms of both P and X. But what is it asking for? It's asking for find the rate at which X is changing as a function of time. So it wants me to find dx over dt. And since this function is in terms of variables that aren't t, I have to implicit differentiate this. I have to take the derivative of this in terms of t, and every time I see a p or an x, I have to use implicit differentiation. So for example, derivative of 5p gives me 5 times dp over dx. Derivative of 3x gives me 3 times dx over dt. Oh, sorry, not dp over dx, dp over dt. My fault. When I differentiate 3x, I get 3 times the derivative of dx over dt. What does this piece require? Product rule. This is going to require product rule. So just be careful about that. Okay, moving on. We don't have time. Ugh. Okay. Differentiate e to the negative x to the 5th over 5. What does this require? Yeah, it requires my log formula. So remember that the derivative of e to the x is just e to the x, right? The derivative of e to the x is itself. But looking at this specific problem, what else do I need? Chain rule. Yep. So when I'm looking at this problem, number 19, e to the negative x 5th over 5, you can put a parentheses around everything inside of your exponent to help you kind of think about, oh yeah, this is chain rule. I have a function inside of my e function. Right now, and this one I can actually do pretty quickly. When I take the derivative, f prime of x, remember the derivative of e to the x it stays the exact same. So I'm still going to have that whole piece, but then I have to multiply it by the derivative of that inside function, which is negative 5x to the 4th over 5. And the 5's can cancel. Cool. Okay. Question 20. This is an important one to talk about, because looking at it, what is this going to require? Product rule. This definitely requires product rule because you have e to the x times natural log of x cubed. So this requires product rule. But I also have this natural log of x cubed. So looking at that, we might think, oh, this also requires chain rule. Right? Because I have this natural log of x cubed, so I'm going to have to use chain rule here. But remind me, don't we have a log property for this? What does my log property tell me I can do? I can just move this 3 where? In front of the natural log. Okay. So instead, before I take the derivative, I can rewrite it like this. E to the x times 3 natural log of x. And that derivative, natural log of x, right? 3 natural log of x, that doesn't require chain rule. That's a nice simple derivative that we can handle a little bit easier. So look for opportunities to use those log properties.
Those won't be on the formula sheet, right? Those rules.
No, log properties won't be on the formula sheet. So those are ones you just got to remember. Okay, moving on.
Wait, the log properties are on.
Log. Oh, they are? Oh, you're right. They are. Log properties are on. So, oh man, we're just giving you everything. Okay. Question 21. Solve e to the 2t equals 1800. Well, what does this problem boil down to? How do I go about solving this? Take the natural log of both sides. Remember, that's why logarithms are so important. Is they're the inverse function for these natural logs, or for these e functions. Okay, so over on the right side, I get natural log of 1800. What happens on the left side? The natural log cancels out with the e, and I'm just left with 3t. And then you can solve for t. Remember, just once again, make sure, I know we're kind of rushing through this. Take your time on the test. Make sure you're reading that blue text. Okay? If you do not round to 3 decimal places, It'll mark you wrong. Even if you did the whole problem right, it'll mark you wrong because you didn't round like they asked you to. So please make sure you're paying attention to any of that blue text. Okay, 22. Suppose that P naught is invested in a savings account in which interest is compounded continuously at 6.8% per year. That is, the balance grows at a rate given by the following equation. So take a look at this. We talked about how exponential functions have this property where the rate of change is proportional to the function value. Notice what this number ends up, or what am I trying to say here? Notice what that number is. It's whatever your rate is. Okay? So if you see something like this, we're talking about an exponential function, and that number is your rate. That's what you're going to plug in for your rate. Notice what this hasn't told you about yet. Starting amount, the initial amount, right? This gives you no information about the initial amount. So if I keep reading, so find the function pt that satisfies this equation. I don't have the initial amount, so I'm just going to use p naught as my initial amount. And I'm looking at option A, right? P sub 0 represents my initial that I don't know, but my rate is that 0.068. Everybody okay with that? So if I keep going, in part B, they give me an initial value. Suppose that $500 is invested. Well, that's what P0 is going to be. P naught or P0 is just going to be $500. And then what is the balance after 3 years? That's what you plug in for T. Okay. Any questions about that one? Oh man. We're doing great now. Yeah, I know I haven't completed it. I'm sure I won't leave. Okay. Present value. Find the present value of $3,000 payable at the end of 3 years if money may be invested at 4% with interest compounding continuously. First of all, you'll notice it's usually pretty specific about this, but the fact that interest is being compounded continuously, what does that mean your base is going to be? Base E, like almost everything that we're working with is base E except for like the amortization, right? That's one of the few times where I wasn't base E. So this one. There's actually two different ways I can go about this. So what's one way I can set this up? Present value, find the present value of $3,000 payable at the end of 3 years. So when do I get that $3,000? After 3 years have passed. So is $3,000 my initial amount or my ending amount? It's my ending value. But that means I don't know what my initial value is. Everybody okay with that? I don't know what my initial value is, but I'm going to have that times e to the, my rate is 4%, so 0.04 times what's my time value?
3 years.
3. So this is one way I can solve for it. I can set it up like this and calculate it like so. Notice that my exponent or my rate is positive because I'm putting the 3,000 over here, and because the 3,000 is what I end up with, and I'm trying to figure out what that initial value is. And now I can solve for P naught. But if I'm ever working with present value, I can actually set it up using a decay function. The other way you can set it up is kind of like you're just working backwards. You can use the 3,000 as your initial amount, but because you're working backwards, I'm going to turn this into a decay function. And that'll get me the same exact thing. Okay. That'll get the same exact thing. So whichever way makes more sense to you. Once again, because I'm working backwards, I use a decay function instead of a growth function. If I decide to just put that 3,000 in for my initial amount. Okay. Very nice. Okay. 24, more derivatives. What are you going to need to use for this derivative?
Properties and derivatives.
So definitely your exponential derivative rules and your log derivative rules, which once again are on your formula sheet. But what else am I going to need to use? Product rule. Yeah, so just always look for that. If you have two things being multiplied by each other, you're going to have to use product rule. Okay. But then when you actually look at each of these derivatives, oh, I can't actually color on that. Makes sense. But when I look at the derivative of 6 to the x, right, just make sure you're using your exponential rule. Don't use power rule for 6 to the x. It's not a power function. It's an exponential function. And then when you take the derivative of log base 5 of x, right, make sure you're using your log derivative rule. That one. Okay, amortization. The first part of this problem is just make sure you know your correct amortization formula, which is given to you on the test. Okay, it does switch around the letters a little bit. Normally, what's I? How did we talk about I? What I guess what letter did we use here instead of I? R, right? The rate. So I guess I is just interest. Your interest. C?
And
We used n because it was the number of times you compound it, but I guess C stands for compound. Right? How many, like the compound. And then the rest is all the same. But same formula. The only thing you have to kind of be careful about with this one is he does make a down payment. So the loan amount isn't $22,550. That's not the loan amount. How do you get the loan amount? Subtract off the down payment. Right? Take off the down payment. Okay, we made it through. We blitzed through the whole review, and some of them we went through a little bit more in depth than others. If you have any questions about any of the problems on this review, please reach out. Please don't be afraid to hop into office hours tomorrow from 1 to 3, or just shoot me an email, and I'd be happy to kind of talk you through any of these. Okay. Okay.